about blockchain secured acoustic signature authentication for military command communication in SWAM intelligence operations. Yep, these are my group mates, and our supervisor is Mr. Kaliwango Marvin. Okay, so background of our problem. So the background of our problem, military operations nowadays making use of SWAM intelligence techniques for for executing their missions. For example, the use of UAVs. These are like drones and maybe robots in some cases. All these need to coordinate and achieve the goals they're supposed to achieve properly. So existing systems are using the command and control infrastructures. This is where a group of technical experts sits at a base, let's say at an official building, and then they command these SWAM intelligent devices like the drones. They command them manually, like through a computer, to go and let's say do what they're supposed to do, let's say bomb an area and then come back. Yep. And the challenges with this is commands can be spoofed, channels can be hacked, and someone else can hack the system and make the drones do all that kind of thing. So our work, we are trying to integrate acoustic signature authentication to make sure that commands aren't spoofed, and then also audio steganography. This hides commands and noise, such that even if someone manages to tap the communication channel, they won't be able to understand anything. And then a blockchain ledger, that's for validating and storing commands in a decentralized way without a central database. And then a SWAM consensus. Yeah, this is to ensure that when, let's say, one element of the SWAM is away or dies out, the SWAM can still continue to function. Yeah, so not waste time on that. Okay. So for the related works, blockchain has been used in military systems. It has been used for secure communication and data integrity, preventing tampering and unauthorized access, enabling trustful and decentralized coordination. And then for acoustic voice authentication, this is more of using voice prints and extracting features from those voice prints to distinguish users, and maybe also detecting deepfakes and spoofing. That's the same thing. Then SWAM intelligence and coordination. This is a concept that inspired by SWAM insects. Things like bees, ants, red ants, termites, insects that live and work together. Yeah. So it enables these systems to be self-organized and fault-tolerant. When one element of the SWAM dies out, that doesn't affect the overall performance of the SWAM. Yeah. And then common algorithms, the ones that currently exist, is the particle SWAM optimization and ant colony optimization. These are more of pathfinding algorithms. Yeah, so for our contribution, we are combining blockchain and acoustic authentication and SWAM consensus. And it's supposed to, this is supposed to work in areas where, the connection is low. Because as I mentioned earlier, with command and control, there is a set of technical experts in a certain centralized office, and they're trying to issue commands to these SWAM elements, which are already in the field. So in case there is a poor connection here, all these operations are hindered. So as we want to make sure that these can go on even when there is these operations can go on without the central command center. Yeah. And do solve this while also ensuring that it's tamper-proof and voice verified. I think I'm going to talk about more of this in the next slide. So these are research questions, so we can ensure secure and verifiable communication among unmanned systems in a swarm without centralized control. And then can a commander's voice be used as a reliable authentication signal in the field? Then how can blockchain and acoustic steganography enhance trust and prevent spoofing in military command and control systems? Those research questions are what we use to generate our objectives, which we shall use when implementing our this work. So without any more, let me go to the methodology and the system architecture. So basically, this slide, you can see how this quantity is split into two diagrams. These are two separate diagrams. The first diagram at the top is on the commander side, like when a commander wants to issue a command to the swarm, let's say to a set of drones to attack. And then the second diagram below is more of what happens after a certain element in the swarm has received the command that the soldier sent. So here, after the commander has said something, a random key is generated and then it's split. Here we end up with a private and public key. And then we also record the commander's message, and then we get a DCIR probe. This is more of it captures the the unique features in the environment, in the commander's voice, such that even if someone tries to deep fake the commander's voice, we can know because it doesn't match our expectation. Because if you offer a command from a field and then someone tries to deep fake your voice from a studio, there will definitely be a difference. So that's the importance of this stage. You get the recording of the commander's voice and the DCR probe, and then we extract features and then we hash it and we combine this. After splitting the keys, we get a key part A and a key part B. Then we assemble the package. Now, when we are assembling the package, here we shall generate a signature. That's for the audible signal. And then the key part B will be attached to the features we extracted earlier. That's the DCIR to form the inaudible signal. So these two are what will be sent to a particular element of the swarm. Actually, the goal is for all elements of the swarm to receive this information. And then they carry out this process independently. So each element of the swarm will carry out key reassembly. They'll recombine these two keys, key part B, crypto, and liveliness check. They will check whether this command that has been issued is a live command. It's not synthesized, it's not deep faked. If it's a live command from the field and from that command using the DCIR features that I talked about earlier. And then when this check is passed, we shall check the attenuation verification and see how many hops in the swarm has this command moved, and does its quality match the quality we expect? If it matches, then that means it's a real command. If it doesn't match our expectation, that means it has been faked. So that's when we come here to our quorum, and then every element of the swarm will vote. It's more of a vote. Those that believe that the command that has been issued is accurate or it's real, it's not faked, they vote for that. Those that believe that maybe the command must have been tampered with and it's not worth implementing, it's risky to implement it, they also vote. And then we calculate 75% of the swarm. If 75% of the swarm agrees that yes, it's a reliable command, if more than 75 agree that this command can be trusted, it hasn't been tampered with, we shall commit that command to the blockchain, and then all the swarms will execute that command. Yeah, and while executing, they will make sure they optimize it. If we can't get the 75%, that command won't be executed. Yeah, that's basically it. And then, yeah, then maybe I can also talk deeper about the biometric feature extraction and alphanumeric key generation. So for the commander device, as I explained earlier, the commander issues a command. We generate a probe. We get the probe emissions and then the multi-channel capture. That's the audible plus the probe echo. Then we extract DCR, the DCR values. Those are more of the biometric features, the voice of the commander, the echoes in the environment, different factors will determine whether this command was issued in the environment we expect it to come from. And then speech factor, extractor, and command hash. Here we compare the voices of the commanders with what we have, and we ensure that it's it. Then we hash that. Then we generate a private and public key. These will have to be generated every session. They are not reusable. And then we split key part A and key part B. We sign the hash, the DCR, and the timestamp with the session private key. And then we assemble the signed package. And that is what we shall send. We send the signed package. Now, when our elements of the swarm receive the signed package, they will have to first embed. They will have to first go through this process and reconstruct the whole message. They get the audible packetizer, that's a text DCR signature plus key pattern. Then they also get key part B, synchronize and mix channels. Then we try to align the timestamps and the timing to ensure that the time when the command was issued and how long it took for us to reach it. We also use that as well to verify whether it's a reliable command or not. Then dual channel broadcast. That's audible plus inaudible key carrier. These are shared with other elements of the channel. Yeah, so this whole process is explained here. It's the same process. This is more of like a flowchart. Dual channel receiver, reassemble both key parts present, yes, no. Local verification vote. Then here we carry out and we measure the audible and inaudible. Yeah, our quorum, the 75% we talked about. If it doesn't reach this, it's discarded. If it's discarded, the command is added to the blockchain. And yeah, that's basically it.